Sorry.
Cos of 0, 1, confirm. Cos of 90, cos of 180, cos of 270, and cos of 360. Okay, so here's what cos theta looks like. Same kind of periodic pattern. It's got that up-downness to it. The only difference is it starts at 1, where sine starts at 0. So this is like a really cool ski slope where you start at the top, you go all the way to the bottom and come back up to the top. Same kind of idea. Again, it's just kind of cool because you've been using these functions for so long, but you probably never knew what they looked like. That's what sine and cos look like. What's the highest possible value for sine? What's the highest it goes on the graph? 1. And what's the lowest it goes on the graph? -1. And what about cos? 1 and -1. And the reason that is back in grade 10 when you first started learning sine, cos, and tan, sometimes you'll do an equation on your calculator, you get an error. And then you're like, my calculator's broken. And we're like, no, no, it's not the calculator. Because go back to SOHCAHTOA. What do you remember about SO? What does that mean? Sine is opposite over hypotenuse. And what do you know about the hypotenuse of a right angle triangle? It's always the longest side. So for sine, you're always dividing a smaller number by a bigger number. And if you divide any small number by a big number, you're always going to get a number less than 1. This is why on the graph it hits a max of 1 and the same at -1. It's because you can't have a sine or cos that's bigger than 1. So what do you remember way back from grade 7? Go way back in your mind. Circumference of a circle. That'd be area. Close, though. Circumference is 2 pi r. So I'm just going to jot that down because it's going to become important in a second. And that's really what our x-axis here is measuring. When we say 0 to 360, that's the circumference of the circle. We've gone around a circle once to get 360 degrees. Well, now we know the maximum radius of the circle is 1. We cannot go higher than 1 or lower than -1 because sine and cos can't do that because of O over h and A over h. So circumference of a circle, I'm just going to put in a value of 1 for the radius. What's 2 pi times 1? Please do not use your calculator. What is 2 pi times 1? 2 pi, right? It's just equal to 2 pi. So what I'm going to do is I'm just going to switch these numbers on the x-axis. We don't actually use 360 because I don't want to measure in degrees. I want to measure in circumferences. So I know a full circle is 2 pi, simply because the radius is 1 because sine and cos can't be bigger than 1. Okay, well, let's go halfway. So 180 is half a circle. If now you know that 2 pi is a circle, what is 180? What's half of 2 pi? 1 pi. Okay, 90 is a quarter of a circle, so what's a quarter of 2 pi, or half of pi? It's a half pi, and we just write that as pi divided by 2, and we call it pi on 2. Okay, same as 1/2 times pi. And the 270, that's 3/4 of a circle, so 3/4 of 2 pi, or you can follow the pattern that's happening here. We have half a pi, a full pi, something, and 2 pi. What's got to be in the middle? 1/2, and we write that as 3 pi on 2. So 1/2 is the same as 3 on 2. This pi stuff is going to become clearer when we get to trigonometry. Again, the reason we just do it is because we know that the radius is 1. We're just using a circumference of a circle. Rather than measuring in degrees, we're measuring in the length of the circumference. Let's do domain and range of, we'll do sine first, so I'm going to match the color if it was purple for me. Domain. Well, This really doesn't start here because I can keep going and have that same kind of idea, and I could keep going in this direction. So what do we say that the domain is if it goes all the way to negative infinity, all the way to infinity? X is an element of the reals, or negative infinity to infinity if you enjoy that notation better. Let's talk about the range. What's the lowest possible value? So we'll look down. -1, less than equal to y, less than equal to, highest value is 1. And again, that just comes from the formula for sine, because it's O over h. H is the longest, can't be bigger than 1. Let's do the same for cos. So again, I'm going to match my color to my cos graph. XCR again. The range, exactly the same. And again, that comes from the cos is A over h. H is the longest side. They're kind of pretty graphs. Looks like a heartbeat a little bit. Okay, let's talk about tan. Tan is the freakiest graph ever. Back to the formula for tan. Tan is O over A. Is either one of those necessarily the longest side? No, so it doesn't have this same idea that it can't go bigger than 1. Tan can be any value in the world. So let's set up our axes. I'm going to use the same values that we just talked about, so those pi on 2, and the pi, and the 3 pi on 2, and the 2 pi. And again, we're just using these values because we're now measuring in a circumference instead of degrees. Okay, so let's start at 0. Same thing on our calc, go tan 0. Tan of 0 is 0. Tan of pi on 2, well, how do you punch pi on 2 into your calculator? Well, there's a pi button, so you're just going to go tan pi on 2, divide by 2. What happens? Okay. Now, this is where your mode needs to change, and this is going to make more sense when we get to trigonometry. But when you go into your mode, when we're measuring in circumferences, that means radians. So instead of degrees being black, you want to make sure your radians is black. So mode, radians, and then quit out of there. Now do tan of pi on 2. And I love all the confused looks because you should have got an error. Did you get an error? Yeah, okay. What an error means in this case is the number is undefined. And what does it mean when a number is undefined? Well, it means that the graph doesn't exist at that number. Ooh, Abby thought of something. What did we draw last year that we already talked about a little bit this year for a number that doesn't exist? What did we draw? How do we represent that when I can't put a point there? Think back to rational graphs. Non-permissible values were points that did not exist. What did we draw for them? It's an asymptote. Welcome back, asymptotes. That's how we show does not exist. Error. Impossible at that point. Okay, pi, so tan of pi. 0. Tan of 3 pi on 2, so you're hitting tan, 3, then the pi button, then divide by 2. Error, how do we draw an error, which is a value that doesn't exist? Another asymptote. I told you tan was a freaky graph. And then tan of 2 pi, back to 0. Well, there's got to be more because we know that graphs approach asymptotes, so there's got to be stuff happening in here. Let's go back to the castrol. Tell me what you remember about the castrol from last year. It's up there, the first blue sheet. It will always be up there. It's not a secret. What do you remember about the castrol? Not much, apparently. A means all are what? positive. What does the S mean? Sine is positive, which means cos and tan are negative. What do you know about tan, or the t in the quadrant 3? Tan is positive, the other is negative. Okay, well that's going to actually help us draw a graph. What this is representing is quadrant 1. From 0 to 2 pi, or 0 to 90 degrees, is quadrant 1. Is tan positive or negative? Quadrant 1. It's positive. So I don't know exactly where this value is going to be, but I know it's above the x-axis, simply because it's quadrant 1 and tan is positive. So I'm just putting a little dot there. From pi on 2 to pi, that's the same from 90 to 180, so that's quadrant 2. What do you know about tan in quadrant 2? It's negative, so I'm going to put a dot below the x-axis. I don't know exactly where it is, I don't care, I just know it's a negative value. Pi to 3 pi on 2, that's the same as 180 to 270. 180 to 270 is quadrant 3. Tan in quadrant 3, positive, so a dot above the x-axis somewhere. And then 3 pi on 2 to 2 pi, that's 270 to 360, so that's quadrant 4. What do we know about tan in quadrant 4? Negative, so there's going to be a dot somewhere below the x-axis. So just to repeat, this is coming from the cash row. Quadrant 1 is positive, so above, negative, positive, negative. Check out this funky tan graph. So I know it's got to go roughly by that point, and I know it's going to approach the asymptote, but remember, it never crosses. Check out the middle section. It approaches from here, crosses through that point, and approaches the other asymptote. I know, so cool. Tan in the last quadrant approaches the asymptote in the bottom. There's our very funky tan graph. Yeah, it's like swishes, yeah. Domain. Well, what did we do with domains last year when we had asymptotes? We went XER, but then we said X could not be whatever the asymptotes are. Same deal here. So I'm going to start with XER. But I'm going to say X cannot be, well, the asymptotes are at pi on 2 and 3 pi on 2. It's exactly what we did last year with rational graphs with asymptotes. Can be everything except these two numbers. What about the range? So look down. What does this arrow mean when it's approaching this asymptote here? Well, it's going to keep going down forever and ever and ever. What does the arrow mean up here? It's going to go up forever and ever and ever. So what does the range have to be? YER. So we brought in a little bit what you knew from trig last year, a little bit what you knew about rational graphs. What we've done in terms of this unit is given you 3 new base graphs. You can have a base graph of sine, a base graph of cos, and a base graph of tan. Now we're just going to do transformations. Let's graph 2 sine theta. Okay, well, let's talk about what the 2 is first. Is it inside brackets? No. Is it in front of the function? Yes, that tells you it's vertical something something. Is it a multiplication, a negative, or an addition subtraction? Multiplication, so that's a vertical stretch. XY goes to X to Y. Start with the base graph, just like we started with the base graph for parabolas, cubics, square roots, all those other graphs. The base graph now is sine. So if you're a coordinate person, we can still do the coordinate table just like before. The values for x are 0, pi on 2, pi, 3 pi on 2, and 2 pi. And those numbers, again, are just a quarter of a circle, half of a circle, 3/4 of a circle, a full circle. Now, eventually, you're going to memorize the y values just like you did for x squared and x cubed and root of x. So they're always going to start with 0, 0 for sine, 1, 0, negative 1, 0. 0, 1, 0, negative 1, 0. Okay, so base graph 0, 0. Pi on 2 is 1 up. Pi is back to 0. 3 pi on 2 is 1 down. and 2 pi is 0. Again, just to repeat, all we've done is just add new base graphs. This one happens to be sine. Grabbing my red pen, because this will be our last graph now, we've got to do our vertical stretch. It says we take the y's and multiply by 2, so I'm just going to change these guys. 0 times 2, 1 times 2, 0 times 2, negative 1 times 2, and 0 times 2. If you'd rather work off the graph, I'm going to do the same thing just in order left to right. 0 times 2 is 0. 1 times 2 has to go up to 2. 0 stays at 0. Negative 1 goes down to negative 2. And 0 stays at 0. Look away. Look back. Did we grab this thing and stretch it from the top and the bottom? We sure did. Does that affect the domain or the range? Good guess. How do you know it's range? Because it's the y values. What would the new range be? Yeah, so we would put negative 2 less than equal to y less than equal to 2. Well, didn't I just tell you sine and cos couldn't be bigger than 1? But that doesn't count when you're doing stretches to it or you're doing translations. That's only the base graph that can't be bigger than 1. So if you're stretching it, hey, you might stretch it bigger and that's fine. We're going to do some compressions where we squish it in. That's cool stuff. Show me your thumb so far. I'm getting good. Let's do some reflections now and some stretches. Okay, the negative out in front. Is it inside brackets or outside brackets? Outside, so that's a vertical something something. Because it's a negative, it is a vertical reflection. XY goes to X negative Y. Oop, negative Y. The 3. Outside brackets or inside brackets? I told you at the beginning of the unit I was going to say that a bajillion times. Outside brackets or inside brackets? Vertical. Multiplication or addition, subtraction? Stretch. Mapping, xy goes to x2y. 3y, because it's a 3. If you're a coordinate person, do the coordinates. Again, the x-axis is always going to be 0, pi on 2, pi, 3 pi on 2, 2 pi. And again, that's just a quarter of a circle, half a circle, 3/4 of a circle, full circle. Again, you'll memorize the y values just like you did the other base graph. They just come from doing the calculator. It starts at 1, 0, negative 1, 0, 1. Just going to the top of my page for left brain people, grabbing my red pen. Left brain people, we like everything to be organized, so I'm just going to put sine and cos up here. Here's the y values you need to memorize. So sine is 0, 1, 0, minus 1, 0. And cos is 1, 0, minus 1, 0, 1. Base graph, so take away that reflection, take away that stretch, we're down to cos, so our values are here, so it starts at 1, goes to 0, goes to negative 1, 0, and 1. Why do we need to know this? Somebody asked me, why do we need to know this? Why, thank you for asking. We're going to do a whole class on why do we need to know this. This comes up all the time in science. This is how you calculate sunrises and sunsets, the moon phases. Remember the blood moon? How do they know it was that day? Well, they use this kind of stuff here. Anytime you're looking at tides of the ocean, so is it high tide, is it low tide, is all based on this. We're going to do something called biorhythms, or what's called biodex. So I'm actually going to get you to tell me how you're going to be feeling on grad day, how you're going to be feeling on your birthday, how you're going to be feeling the day after your birthday. We can do all that just using these graphs here. There's tons of applications in biology, chemistry, physics, all that fun stuff. Got a little too excited there, didn't I? A little bit. Okay, reflection again. If you want to work off the points, work off the points. If you don't, wait for me a second. Changing the sign, so 1 goes to -1. 0 does not go to -0. -0 does not exist, it's just 0. -1 goes to. 0 goes to. And 1 goes to -1. Oh, thank you. Applying the new points, again, if you're not a coordinate person, you're just coming to the graph and you're just flipping this over the y-axis. So anything above is going to go below. Anything on the x-axis stays. Below goes above, stays below. So all I did was flip it over the y-axis, or the x-axis. Just repeating again, I'm not doing anything different with the transformations. I'm just doing it to a different base graph. Okay, going to red pen because our stretch is our last one. Again, you can just take these y coordinates and multiply by 3. If you're going to do that, you do that. I'm going to work off the graph for the graph people. Again, I'm just going to go in order and multiply by 3. So -1 times 3 would go down to -3. 0 stays where it is. 1 goes up to 3. 0 stays where it is. And -1 goes down to 3. Now, physics people, you have to remind me, with a sound wave, when the amplitude gets higher, does that mean higher pitch? I can't remember. Did you guys talk about that? Yeah. Again, that's all they were doing, by the way, in physics, is they're just doing transformations of graphs. They just call it fancy stuff. Two definitions you need to know. The first one is the height of a trig graph between the max and min value. The height of a graph between the max and min value. I'm just going to put, not an asymptote, but I want to just kind of highlight the x-axis, so I'm just doing it dotted because it's not really part of the graph. So this word, which I'll give you in a second, is either from that, what we call the center line, to a max, or it's a center line to a min value. Doesn't matter because they're all the same distance in this graph. So if I were to measure that center line to the highest point or the lowest point, how many units is it? It's 3. We call that the amplitude. If you play guitar, or you've seen somebody play guitar, what do they plug the guitar into? An amp. That's why, because they're amplifying the sound, because what they're doing is making the sound wave bigger. That's why it's called amplitude. The width of one cycle of the graph. By definition, a cycle of the graph is either a min to a min or a max to a max. It doesn't matter because it will all be the same distance. So for this graph, I'll go from a min all the way to the next min. So that's called a cycle of the graph. So the lowest point to the next lowest point, or I could have measured highest point to the next highest point. Physics people, it's called the period of the graph. Also known as frequency to physics people. We're going to come back to those two words, but you're going to hear us always talk about amplitude, period, domain, and range of a trig graph. It's kind of the 4 values that we state afterwards. Amplitude is the height. Period is the width. Domain and range are the x and y values. Okay, let's do some translations. 2 cos theta plus 4. The 2, what is it? I like it, vertical stretch. XY goes to? Turn and talk. Tell someone, how did you know that was a vertical stretch? And because Abby said so is not the right answer. Just saying. What's the plus 4? Turn and talk. Whoever just didn't talk, who was the listener, is now the talker. Tell them, how did you know it was a vertical translation? What's the base graph? So strip away all those transformations. What's left if we take away the 2 and the plus 4? Cos. Okay, how do we draw a cos graph? Well, you can either do table of values, or again, you'll have these memorized after we've done a couple questions. Cos in order starts at 1, then goes to 0, then to -1, then to 0, then to +1. I don't know why I suddenly did it in pencil. There just happened to be a pencil in my hand. Do we do the stretch first or the translation first? Stretch first, because bed mass, right, left to right. So we're going to do the stretch first. That means we're taking the y values and timesing by 2. So 1 times 2 is going to go to 2. 0 times 2 stays. -1 times 2 goes to -2. 0 stays. +1 goes to +2. You'll notice these are nice, like, curvy lines. They're not straight lines, so there's no V's, there's no points. They're nice, like, smooth curves. Grab my red pen, because this will be our last graph. I'm going to take all the y values and count 4 up. And I'm going to run out of space, but that's okay. 1, 2, 3. Left brains will understand that it really bothers me that there's not enough space. Again, for music and sound people, what this is the pitch. So we've raised it an octave or part of an octave when we move it up. Look away. Look back. Did we stretch the heck out of it, and then did we move it up? Domain. And I just realized we made a mistake on the last one. We can't use x over here. Why? Because the variable is. So this should be theta ER, and we'll go back and fix those ones before. Should be theta ER, I just realized, because there's no x. So let's just go back. Where were we here? Let's change this to theta, and to theta, and to theta. Which, if you've never been in my class before, let me give you my little theta lecture. Theta is a Greek letter. What English letter is it the equivalent of? It's a small t. So sometimes small t's are kind of written like that. That's kind of where it stems from, right, and kind of evolved to this. And I like to spell it. And the reason I like to spell it is because I had a student graduate and go to university thinking it was feta, like the cheese. It's not. It's theta, not feta. Please don't tell your university professor it's feta. And if you do, don't tell them I taught you. Range. Okay, so we need to go from this red graph. What's the lowest point? Where's that minimum value? Oh, 3, 2, 3, 2. 2, and what's the highest value? I heard 6, I heard 4. 6. Even though it's off our graph, we would have taken 2 and counted 6 up, or counted 4 up to be at 6. Do you see how we're doing the exact same transformations? We're just changing what the base graph looks like because these are really funky, cool graphs. What is this? This looks like another language. Well, it is, because those are both Greek letters. Okay, we're going to identify the transformations just like before. This stupid pi guy, inside brackets or outside brackets? That means it's horizontal. Multiplication or addition, subtraction? Addition, subtraction, that means it's a translation. Pi units to the right, and that scares me, so we'll talk about that in a bit when we do it. The -1 outside the brackets means it's vertical. It's a subtraction, means it's a translation. 1 unit down. Take away those two things, the horizontal, vertical translation, what's left? Cos. Draw the base graph of cos. What does this mean, pi to the right? Well, pi in terms of this is just 2 units. Now, I don't mean 2 of these individual ticks. I mean this is a pi on 2, this is pi. So all I'm doing is I'm moving it a half circle over, okay? And then I'm going to move it down. So let's do this one together. Right now, the x value is 0. If I move it to pi, it's going to go all the way over to here, and it's going to drop 1. I went from 0 to pi because I added pi, and I dropped at 1. So beginning of the circle, went to half the circle, dropped down 1. Pi on 2, if I add pi to that, is going to be 3 pi on 2, and it's going to drop down 1. So I took pi on 2, moved him all the way over to 3 pi on 2, dropped him down 1. Pi plus pi is going to go all the way to 2 pi, so I went 2 of these units over, and it's going to drop down 1, so I'm at -2. If you'd rather do that with the coordinates, then do it with the coordinates. I just shove this thing over. The problem with these sine graphs, or cos graphs, is because they're what I said before, periodic, is that they rise and fall over and over. I can't have just an empty part of the graph here. They don't work that way. So I know I have this section of it. What is this side going to look like? So if we think in terms of the base graph, and I work from right to left this time, it went from 1 up here to -1 to 1. What would it have done over here? So if I went from the top to the bottom to the top, what would have happened over here? It would have been to the bottom. So when we shifted, we have the bottom, the top. What would have happened here? It would have been a bottom. So all I'm just using is the features of the graph just to fill it in back to the x or to the y-axis. So in essence, I'm just going to highlight this a little bit, make this darker. That's the section of the graph that we moved over. It's that hill part to it. We moved it over and we dropped it down. I should have done it in red. Left brains, you understand. Left brains. Yesterday I was ripping a page out of a notebook and I was ripping off the little, the things you get on the side, and I'm ripping, and the very end of the corner ripped off. I'm like, oh, and I threw out the paper. And the right brains are like, what? I'm like, no, but it's ruined because I ripped the little corner off of it. Right brains didn't get that. No. Domain. So we're looking left to right. If your brain's not sure, put the arrows, because we know it goes on forever and ever and ever. And you want to say XER, except we have to match the variable in the equation. theta ER. Look down, look up for range. What's the lowest value? Where's that low point? Where's the min? -2. Where's the highest point? Where's the max of the graph? 0. I think that's it. Nope, we're going to do some inverses. Draw the inverse of y equals sine theta. Okay, inverses we did, what's today, Thursday, Tuesday. Turn and talk. Remind somebody what's an inverse. Lots of good conversations. I heard it's the little -1. It's that or the diagonal reflection. It's where you flip the coordinates. That's exactly what it is where we flip it. So what we're graphing, and you've probably never thought about what this looks like, is when you do that inverse sign on your calculator, what does it look like? That's what we're about to see is what does this look like? Base graph is sine theta. So remember sine theta goes 0, 1, 0, -1, 0. Okay, 0, 0, flip those coordinates. 0, 0. Okay, the point's going to stay the same. Pi on 2 and 1, flip those coordinates. 1 pi on 2. The problem is where the heck is 1 on this thing? Where the heck is pi on 2 here? So it's actually easier when you're doing inverses of trig graphs is to draw yourself new axes, and we're just going to switch the labels on them. Otherwise, you have to start estimating. So all I'm going to do is flip it. I'm going to put 1 on the y-axis, x-axis, I just lied. And I'm going to put those 4 values on the y-axis. So pi on 2, pi, 3 pi on 2, 2 pi. Again, you can do it on the regular axis, but then you have to start estimating where is 1. I don't know what's going on. It's easiest just to redraw these axes. And I don't know why I did it in pencil. I need to stop picking up my pencil. Okay, so 0, 0 we know is going to stay at 0, 0. Pi on 2, 1 is going to become 1 pi on 2. Pi 0 becomes 0 pi. 3 pi on 2 -1 becomes -1. Now, we don't typically draw the left-hand side. I like to put it in there, even though you won't see it in the book, because it's how my brain works. So the brain will not, or the book will not have this left-hand side, because we tend just to do the right-hand side for cos and sine. And then pi on 2, or sorry, 2 pi 0 becomes 0, 2 pi. So take a look what happens to this super cool graph. There's your first inverse cos. When you inverse cos on your calculator, that's what it looks like. Again, the book tends just to show you that one little bump because we tend not to do the left-hand side. I like to show both just because I like both the max, the min, and that up bump and down bump. How are we doing so far? Domain of this babe. Oh, I should have done it in Word. Okay, domain. -1, less than or equal to, except we don't have an x in the equation, theta less than or equal to positive 1. What about the range? Again, keeping in mind there's arrows. It goes on forever and ever. YER. And just like when we did inverses on Tuesday, you'll notice the domain and range flip. Domain of the original becomes range of the new one, et cetera, et cetera. Let's look at inverse cos. Okay, same procedure. Let's start with the base graph of cos. Draw the base graph of cos. Already got it memorized. Oh, I kind of missed pi on 2 there. Now again, you can do it on the same set of axes. It just makes it harder because where is 1, where is pi on 2? I just like to redraw it. Again, the book typically doesn't do the left-hand side, and you'll figure out why once we talk a little bit next class. I like to put that -1 in there because my brain likes to see the whole thing. And then my pi on 2, my pi, my 3 pi on 2, 2 pi. Okay, so the first original point is 0, 1. Flip it. 1, 0. Pi on 2, 0 becomes 0 pi on 2. Pi minus 1 becomes -1 pi. 3 pi on 2, 0 becomes 0, 3 pi on 2. And 2 pi 0 becomes 0, 2 pi. No, I just lied. 2 pi 1 becomes 1, 2 pi. Again, the book will typically sometimes just show you this, which I think is a stupid graph. I have to do the left-hand side because I need that snakiness to it. Do you notice how these kind of look like snakes? Okay, and it's the coordinate plane. We call it snakes on a plane. I actually got a chuckle. Nice. Domain. Left and right. And the range. The last example we're going to leave because this actually we need to do after trigonometry, and we haven't done that, so we'll come back to that in trigonometry because you're probably like, what? What is this? It'll come in Unit 3 for you guys. Getting this? Kind of getting this, not getting this. Show me where you are on this. Good. Practice questions on 521. Pick the scariest question you can find. Snakes on a plane.